Very excited to be talking with you all today and to really kind of dive into kind of a 201 on advanced reactor technologies. So with that, I always like to start my presentations with a couple of main takeaways. The first one is that I think as folks are starting to look at advanced reactors, one of the things to keep in mind is that it's possible to start to kind of characterize the different advanced reactor concepts that are currently under development by private companies by taking a look at things like their coolant type, their fuel type, and their power output. And these can provide a lot of really interesting insights on things like their safety case and potential economic uses in the future. And that can be one of the really good factors to help you kind of evaluate, is this technology for real? Or are there things that this technology is going to have to work through on its path to commercialization? The second is that, and this is something that I think is just really important for the advanced reactor space more broadly, it's that some of the design choices that we're making now for advanced reactor technologies can really help kind of reduce the hazards of nuclear energy moving forward, especially when compared with the conventional large light water reactors that we're using today. And that finally, this characterization and evaluation of advanced reactor concepts and companies is possible by taking a look at their reactor design and the kind of choices they're making with their business plan. And this can hopefully help you get a little bit more information when you're starting to evaluate what are companies that I'm interested in working with, maybe joining, or if you're interested in starting a company of your own in the future, what types of things do you want to make sure you keep in mind so you can start to build a more kind of credible business case for your technology. And so with that, let's go ahead and start jumping into the actual advanced reactors themselves. So the place that I always like to start when I'm talking about any advanced reactor technology or really trying to evaluate any new company in the space is looking at three big things. What's their reactor coolant? What's their reactor fuel? And what's their reactor power output? And these are characteristics that I think can help kind of differentiate the different advantages and challenges of advanced reactor technologies in the space. So while it might just be kind of three kind of bulk characteristics, if you know those and you can learn and you know a little bit about advanced reactor design and operation, then what you're able to do, if you can click one more time, is that you start to get information on things like their safety case, their technology use cases, and what are the business opportunities. Because it's connecting these kind of underlying technical factors to how the reactors themselves might operate in the future. So, for example, if we click forward, let's take a look at how power output might relate to something like the reactor safety case. And so if we kind of think about it, if we started with a microreactor, for example, this is a small modular advanced nuclear reactor, let's say smaller than 30 megawatts electric. Well, one of the things that we're going to know right off the bat with a reactor of that size is that it's going to have a reduced reactor post-shutdown heat load. Essentially, the amount of decay heat that's being produced by that core is going to be orders of magnitude smaller than a large light water reactor, just simply due to its size. And the important implication there is when we're thinking about the safety case of these technologies and their deployment strategies, we're going to have a significantly reduced reliance on reactor heat removal systems. So in conventional large light water reactors, we think of things like having your emergency core cooling system as being a very costly, challenging to engineer system. But with a microreactor, that might not be the case. And so we can start to think, okay, how does this reduced reactor size ultimately feed into maybe a potentially easier path through licensing, maybe a reduced design or safety requirements, or open up maybe different use cases and markets that otherwise wouldn't have been possible for a reactor that had a really large post-shutdown heat load. So what I like to do is kind of dive into each one of these three, the reactor coolant, the reactor fuel form, and the reactor size, and talk about what some of the implications of these might be with some of the major things that are out there and how we can compare it to some of the reactor technologies that are currently operating today. So the first one is going to be the reactor coolant. And really, it affects every part of your reactor, the temperature, size, and the safety characteristics. So in the conventional nuclear reactors we use today, primarily light water, normal H2O. Conventional water, despite maybe not being the flashiest coolant, is really nice for two main reasons. One, we know a lot about water. We've got really, really well-characterized properties, and we have a lot of engineering experience with high-pressure water systems. We've been using it for over 100 years. We know how to design and build these. That being said, there are a few challenges with it. One, it's got a very low boiling point, needs to be operated at high pressure, so that creates some mechanical system challenges and some safety system challenges. It's got a low energy storage capacity, and by that I mean, if you start to heat up water, it very quickly can vaporize and boil, change phase, and then that introduces some design and operational challenges. And finally, water can be reactive under some conditions. If you take certain metals and you start to heat them up, You can have oxidation reactions where the oxygen is literally split off your light water coolant and produces hydrogen gas, which introduces some additional challenges. Also, water likes to eat through things, so it's something you have to design for. As we start looking to advanced nuclear reactors moving forward, we now start to kind of open up the space of what are different reactor coolants that we could use. And the important thing to think about is how might these different coolants start to provide us kind of changes to things like the operating temperatures. Can we operate at higher temperatures? The reactor size, and what the potential safety characteristics are. And so now we're going to dive into kind of each one of these four major advanced reactor coolants: molten salts, gas coolants, liquid metal, and heat pipe, and talk about what some of the implications might be. So the first one that we'll talk about is molten salts. And for the purpose of this conversation, we're really going to limit it to solid fueled, liquid cooled reactors. So when I talk about molten salts here, I'm specifically talking about the coolants and not actually about reactors that might dissolve the fuel in their coolant. We can talk about those in the Q&A afterwards. But one of the really big things when you take a look at molten salts from the outset is that they're a fantastic coolant because they've got an extremely high boiling point, can operate at low pressure, have very high heat transfer, and can retain radionuclides. And so these come with three major advantages. You basically end up with a coolant that can absorb a lot of heat, won't boil, and so if you have an accident or if you have some condition where you lose the ability to cool the reactor, that coolant can absorb a lot of that thermal energy from decay heat. And finally, it retains radionuclides. So if you do have a fuel that potentially suffers a failure or leaks radioactive material, those radionuclides that might normally be released to the reactor system in a light water reactor can actually be chemically bound by the salts that you have. In this case, the example of salts that we talk about are FLiBe, which is a fluoride lithium beryllium salt, or FLiNaC, which is a fluoride lithium sodium potassium salt. And so these chemical properties become a huge advantage for molten salt reactors moving forward. That being said, molten salts do have some downsides. For example, the first is that we have a lot less experience operating large industrial systems that use these types of molten salts. They come with increased corrosion and chemical hazards, and this can ultimately make the systems harder to engineer and maintain. And so these are kind of interesting challenges and drawbacks as you're thinking about trying to deploy molten salt reactor technology. Yes, it might have some advantages on the coolant. It might allow you to design a nice, compact nuclear reactor, but you're going to have a lot more questions related to the qualification, the design, the prototype, and the long-term operation of your systems. So one example of the reactor technology that's using this is Kairos Power. So Kairos Power is using a liquid fluoride lithium beryllium, that FLiBe salt, to help cool its Hermes test reactor. And so this enables a very small, compact nuclear reactor and a very excellent safety case in the idea that it can help kind of prevent the release of radioactive material in any accident situation. But what Kairos is having to do is undergo additional testing through non-nuclear and nuclear prototypes to try to provide validation on their essentially system design, because we don't have that much experience with the coolant, and then also on the longer term operation. So we understand that this reactor could operate not just for a couple of months, but for a couple of decades safely. And so Kairos Power is being very deliberate with their testing strategy to help overcome these challenges associated with using FLiBe coolants. We can head to the next slide. So the next kind of major advanced reactor coolant that we're seeing described is gases. And so the most common gas that we'll have is helium. There's a long experience with operating nuclear reactors with helium, and there are a couple of major advantages of this. First, no boiling concerns. In conventional light water reactors, we're really worried about what happens when your water coolant boils, because it changes the heat capacity, it changes the heat transfer, and it can change the way that the system is interacting with the fuel. If you have a gas reactor, no need to worry about it. It's already gas and it will always be gas. It's incredibly well characterized. There's a lot of experience using helium gas systems, and it's incredibly non-reactive gas. It's the joy of being one of the noble gases over on the right side of the periodic table. It's not going to react with anything. And we have a lot of experience using helium gas. Specifically, there was the Fort St. Vrain nuclear reactor that was operated in Colorado in the 1970s and 1980s in the United States. And that was actually a high temperature gas reactor that was operated with helium. So we have modern experience in the United States using these systems. That being said, it also has some drawbacks. The first is that just running gas over nuclear fuel really is not that efficient for heat transfer, and it has an extremely low energy storage capacity. If you start to heat up gas, the temperature will increase dramatically based on the volume and mass of gas that you have. And so what that means is that you can't rely on that gas to help kind of absorb that heat that might be released if you lose the ability to cool the reactor. And so you have to start to think about how can you design your system differently so it doesn't necessarily rely on the properties of the coolant to ensure safety under all conditions. So an example of this is the X-Energy reactor. So X-Energy, specifically their XE100 reactor, is a helium-cooled gas reactor. And so in this case, they run helium coolant over their nuclear fuel, and that's going to be able to remove the heat. The other advantage is that gases can, because they don't have a boiling point, can operate at extremely high temperatures without the worry about corrosion. So let's go to the next coolant. So liquid metal, this is a really interesting one. So what we can look at here is that we're, instead of running, again, liquids or salts or gases, we're actually taking liquid sodium in most cases and running that over our nuclear fuel to remove the heat. And so the advantage of liquid sodium is that it has an extremely high boiling point, thousands of degrees C. It has excellent heat transfer, and it has very high energy storage capacity. So that sodium can absorb a lot of thermal energy, which makes it both efficient for designing a reactor, but also means that if you have a reactor power transient, if you have changes in your core power level, or you lose the ability to cool the reactor following shutdown, that coolant can absorb a lot of that energy without having huge changes in temperature. So it becomes a really interesting safety characteristic. It also allows you to build a very tight and small reactor. We have some engineering operating experience with this. The US has operated a number of sodium fast reactors, and there have been a number around the world. So we have some experience. The main challenges are the coolant is reactive. So if anyone has ever had any knowledge of looking at sodium-based systems, what happens with liquid sodium when it comes into contact with water? Everything catches fire, and sometimes it explodes. And so when you have a highly reactive coolant, you have to start to think about how can you safely design this system to prevent any types of those interactions and mitigate them if they do occur. And so this can make your systems a bit harder to engineer and harder to maintain. And you have to think about the interfaces between your systems that are using a liquid sodium coolant and the rest of your plant. For example, you might not want a power plant that directly interacts a water balance of plant or steam cycle with a liquid sodium interface, because the steam generator between liquid sodium and liquid water would just be asking for trouble. And so there have been different proposals on how to kind of get around this. And one of the companies that's looking at using this liquid sodium coolant is TerraPower. And so TerraPower, with their Natrium reactor, is looking at doing a liquid sodium cooled fast reactor. And so in this case, what they're doing is they're running liquid sodium over their core and then having it interface directly with a molten salt energy storage system. And so because the liquid sodium is so effective at transferring that heat and storing that heat, it becomes a highly desirable interface with that molten salt storage system. So it becomes a really good fit as a way to try to absorb heat, store it, and use it later. And we'll talk a little bit later about how that fits into kind of what TerraPower's design regime is. And finally, the last one is heat pipes. And this is a little bit of an interesting one, where instead of having liquid coolant removing the thermal energy from our fuel, we're looking at using solid components called heat pipes. And so a heat pipe is essentially a long sealed tube that uses an intermediate fluid to essentially help kind of move heat along the length of the tube. And so you can imagine at one end, you are either boiling, vaporizing, or otherwise changing state of your kind of sealed working fluid. The working fluid then travels via pressure differential down to the cold end, where it then either condenses, cools, or otherwise changes state and transfers that thermal energy. And so you basically end up with a way to move heat efficiently from one place to another without the need for having large amounts of flowing liquid or gas. And so this can be a really good advantage because it can operate at a higher operating temperature. There's no moving coolant, so you don't have to worry about your loss of coolant accident. You have multiple reactor heat transfer paths. So instead of relying on one giant tube that's moving all your coolant, you instead would have a large number of these small heat pipes that are moving the energy. So the failure of one isn't going to lead to kind of a catastrophic challenge to the reactor. And finally, you eliminate a lot of the corrosion concerns. You don't have to worry about what happens when that liquid water or sodium or salt flows over your pipes. It's just one sealed unit that you're looking at. The challenges of those, however, is that heat pipes are going to be a lot less efficient, at least in their current form, than heat transfer with liquid coolants. And that's just because ultimately you're moving a lot less material and you can move a lot less thermal energy. we also have more limited operating experience with these technologies. And so it's not necessarily clear how they're going to operate over long periods of time or in some radiation environments. That being said, for all these advantages, there are a number of companies that are looking at it. So for example, if we take a look at Westinghouse, they're looking at using the heat pipes as the basis for their Vinci reactor. They have a solid core that they then use heat pipes to remove that thermal energy from and transfer it to a balance of plant. And so the idea is that it can create a very compact and simple design that doesn't necessarily require the pumps and valves and fluid control systems that you would historically have in a commercial nuclear reactor. And so it's one of these really interesting things that's maybe pushing them to a slightly more novel design. That being said, with heat pipes, they're never really going to be designed, at least in their current state, at moving large amounts of energy. So I doubt you'd have a reactor that would be a 1,000 megawatt reactor that use heat pipes. Right now, they're intended for much, much smaller designs. And so with that, let's move to the next category, which is looking at reactor fuel. Again, reactor fuel, much like a coolant, can have a huge impact on what temperatures you can operate at, what are the economics, and what are the safety characteristics. So for the reactors that we use today, we use ceramic low-enriched uranium in a form of UO2. And with this existing fuel form, it's really well characterized, it's a fairly stable fuel form, and it's easy to manufacture. We understand how this fuel behaves under a wide range of conditions. Challenges? Well, it's got really poor heat transfer. With any type of ceramic, you end up with a low coefficient of heat transfer. And so you basically end up with large temperature gradients that occur over the fuel. This can lead to a lot of stresses and cracking within the fuel and potentially allow for the release of some radionuclides. Additionally, these types of fuels require metallic cladding because you couldn't have an interface between the uranium oxide and the water coolant in existing reactors. And so this metallic cladding layer then becomes a potential opportunity for corrosion, for surface interactions, and it becomes something you have to manage. So it's not necessarily desirable. As we start looking at advanced reactors, we now start to kind of open up the space and say, what are different ways that we could have physical fuel forms? And what might some of the advantages be? And so for this presentation, we're just going to touch on the top two, specifically the metallic fuels and the triso fuels, but happy to answer advantages later about some of the molten salt fuels and the carbide fuels. So the first one that we'll talk about are metallic fuels. And so with a metallic fuel, instead of using a uranium oxide, a ceramic, what we're interested in doing is using a uranium alloy, like a uranium zirconium alloy. And so these metallic fuels have a couple of major advantages. First, because you can essentially have better heat transfer across your fuel, it can lower that reactor centerline temperature and allow you to operate your fuel at a net higher power than you would with a uranium fuel. You can imagine one of the challenges in a oxide-based reactor, in the conventional reactor, is that if you've got a multi-100-degree temperature differential between the surface of your fuel and the center of your fuel, you're trying your best not to melt that fuel. In a metallic fuel, there's an opportunity to operate it at a net higher temperature and kind of achieve an overall higher thermal efficiency for your system. And so these metallic fuels can potentially bring a lot of advantages, and we do have some operating and engineering experience using these. The challenges, however, is that the operation of these fuels under a wide range of conditions hasn't been fully characterized. We have thousands of reactor years of experience using oxide fuels, and we understand how they behave under a wide range of conditions. These metallic fuels, however, we haven't necessarily put through the same level of testing. And so there's some question about if you left this fuel in a reactor for a period of years or maybe even decades, in some designs that have kind of life of core or life of plant cores, how are these fuels going to behave? And so it's a question that we're still working through. And so these uranium fuels become a really interesting opportunity because they also enable the use of more fast reactor technology. And so this is one, again, we can talk about later about the difference between thermal spectrum reactors and fast spectrum reactors if folks are interested. But the idea is it potentially opens up kind of a new regime for thinking about the operation of your fuel under a wider range of conditions. So again, this metallic fuel fits really well with TerraPower's design, where they're interested in using that sodium coolant, because the sodium coolant would ultimately match very well with the metallic fuel and would have a lot of the similar operating characteristics. So it's something where you can kind of see it becomes a bit of a natural fit there for them. The next type of fuel I want to hit on are triso fuels. And so these are a really, really interesting technology where what they do is they take small particles of uranium oxide and then coat it in layers of carbon and silicon carbide. And so TRISO is actually an acronym for tri-structural isotropic fuels because it describes that little uranium kernel wrapped in layers of protection. And so what this fuel does is it has a high level of stability, excellent radionuclide retention, and some proliferation resistance. Essentially, that little particle is stable at incredibly high temperatures. It helps capture any types of radionuclides that would be released during the fission process because the radionuclides would have to make it through those multiple layers of protection before they even exited the fuel kernel. And it's proliferation resistant because you have to do a lot more physical and chemical work to try to extract any special nuclear material that might be in the fuel. And so this becomes a really interesting opportunity to say, hey, how do these TRISO fuels potentially fit into something that is a high temperature, high safety application? The downside of TRISO fuels, however, is that it's a much more challenging fuel production process. Rather than taking a uranium oxide and squishing it into a pellet, you have to think about how to make sure that every single one of your particles have the exact same layers and that you understand what the constraints and limitations are on that engineering process. So there's been a lot of work to try to develop TRISO fuels, and they end up being the basis for a lot of different reactor technologies. So for example, if we take a look at the X-energy reactor, they've selected the TRISO fuel as something that makes sense for them. Because the helium in the X-energy reactor can go to extremely high temperatures, they've selected a fuel that is also stable to really high temperatures. So it allows them to kind of achieve a much better economic condition for their reactor because they can operate at higher temperatures that lead to higher efficiencies and other potential industrial use cases. And so you can see here, there's kind of a natural synergy between what they wanted to select for their coolant and what fuel they're using so that they line up in the best possible way. The last thing that we'll talk about before we kind of do a few examples of how these things all fit together is reactor power. And reactor power is absolutely critical because ultimately it's going to affect the physical size of the reactor, the construction opportunities, siting, and some of the different safety characteristics. So when we talk about conventional nuclear energy in the United States and largely around the world, we're generally talking about very large reactors. These reactors are many hundreds of megawatts, and most of the times are over about 1,000 megawatts electric. And so with that, it comes with a few kind of challenges related to the size. If we start talking about advanced nuclear, we start seeing them being operated in a much wider range. We might have large reactors, 300 to maybe 1,000 megawatts, the small modular reactors, maybe 30 megawatts to 300 megawatts, and then finally microreactors, things lower than 30 megawatts. And so you can see we're really kind of spanning about 4 orders of magnitude here in terms of your power output. Now, this reactor core power is really important for a number of reasons. One, it's going to affect the physical size of your system. You can imagine the footprint and the amount of nuclear fuel that you're going to need for a small microreactor is going to be very different than a reactor that's producing 100 times or more the amount of power. Second, as you start to decrease your reactor power, you start to reduce a lot of things related to safety, specifically the amount of actual radioactive material that's in the core that could be released during an accident, the amount of thermal energy that's going to be released from radioactive decay following shutdown, and the amount of energy that potentially could be released in an accident. And so what this means is that the safety systems and safety requirements we have for very large reactors to help accommodate things like how to ensure the reactor fuel stays cool after shutdown might not be issues for smaller reactors. You might be able to use things like convection, conduction, or radiation to try to remove the thermal energy without the need to have forced convection from backup pumps or other backup systems. Additionally, if you're starting to look at siting, well, the worst case release from a very small reactor is probably going to be a much, much smaller potential impact on the community than a reactor that's 50, 100, 200, 500 times larger. And so this creates a really interesting paradigm where you can start to think, okay, does change in the reactor size potentially change the siting requirements? And could we integrate nuclear into places where otherwise we would be concerned about what the footprint for the safety would be? And so you can see this is kind of the final piece that if you start to understand, you start to get an idea of what this reactor is actually being designed for. And we can talk a little bit about later on some of the impacts on reactor size. So finally, I think you hopefully can start to see how if you start to understand some of these reactor characteristics, like the coolant, the fuel, and the power output, it starts to give you more insights into how the reactor is going to operate. So let's dive into a couple of examples. So the first one is, we've already talked a little bit about them, X-Energy's XC100. So here, if we kind of go down those three characteristics, we can take a look and say it's a gas-cooled, TRISO-fueled, small modular reactor. And what that starts to tell us is, okay, they select TRISO fuel and gas-cooled and SMR, which means that, hey, it's going to be a smaller reactor that can operate at a higher temperature that's got an excellent safety case. And so you can start to see now, okay, what they're really going to be aligning for is places where they might have a need for really high temperature heat. They have a very high expectation of safety, and the deployment of smaller units might match up with it. And that starts to kind of point you to why X Energy is really looking at the industrial heat market as a potential path forward for their technology. In their partnership with Dow Chemical, specifically looking at deploying the X Energy at the Seadrift site in Texas, this type of reactor would line up really well with the needs of a chemical producer who want high reliability, high temperature process heat, that want to be able to deploy it based on how their demand is changing at their site, and want to ensure that it's a very safe reactor that matches up with the safety characteristics of the plant. They don't want to introduce a new energy source at a chemical facility that's ultimately going to raise the hazard profile of the facility. So you can see here now how these three pieces start to play together, and you can kind of understand why X Energy is targeting the markets they are. Let's go to the next slide. So Natrium, we've got a slightly different approach. They've gone for the sodium-cooled, metal-fueled, and large reactor. And so what you're looking at here is you now have a technology where they can operate at high temperature consistently. It can operate at a high power because it's got that combination of the really efficient sodium coolant and the really effective metallic fuel. And it's something that can store a lot of thermal energy and integrate well and efficiently with energy storage systems. And so what they've done is they've now created a system that's more optimized for kind of long-term energy production. And so they've got a really high reactor heat core capacity. They've got reduced shutdown requirements because the reactor can survive a lot of different power variations while remaining in a stable state. It can integrate really effectively with large amounts of thermal energy storage. And so you now see why TerraPower, with their Natrium design, is looking at kind of pursuing markets, specifically with their Kemmerer, Wyoming project, to integrate into more variable energy production. Because now you have something that can really kind of match grid conditions and provide energy on demand when it's needed, and use that thermal energy storage system to help kind of balance fluctuations that you see in the grid. And it's a very different market than what X Energy is going for. And a lot of that ultimately derives out from the technology they've selected. If we can go to the next slide. Kind of the third example is if we take a look at Kairos Power with their Kairos Power FHR, it's a salt-cooled, TRISO-fueled small modular reactor. Again, here they've selected an interesting set of combinations. By using the salt-cooled and the TRISO-fueled, they've designed a reactor that's going to be extremely effective at retaining radionuclides. So even under accident conditions, one, the TRISO-fuel is going to be a really effective barrier to any types of release of radioactive material. And then the coolant they've selected is almost a secondary barrier for trying to retain it. And that means that they're potentially going to have a much lower reliance on their reactor containment systems, which could ultimately help kind of reduce the cost of these systems because they've got multiple independent barriers to release radioactive material. By using a small modular reactor, it's kind of an additional fact where they're lowering the amount of material available for release. So this this Kairos Power design ultimately becomes an incredibly safe reactor, has the potential to become an incredibly safe reactor because of this combination of factors that they've used. And then the question would be, how does that ultimately integrate in a commercial sense with power production or other industrial heat needs? The final example that we'll look at is the Aurora Powerhouse. And so this is a really interesting heat pipe cooled, metal fueled microreactor. And so with the Aurora Powerhouse, they really selected a technology and a set of choices that tries to kind of eliminate the safety risk and create the minimum viable kind of nuclear power plant. By using a metallic fuel, they have a fuel that's stable to fairly high temperatures and very effective at moving heat. They've got heat pipes, which eliminate any type of loss of coolant accident and help kind of reduce the potential opportunities for accident scenarios. And by using an incredibly small reactor, the amount of decay heat that they would have to remove is minimal. Oftentimes, I've heard the amount of decay heat from the Oklo Aurora Powerhouse as being similar to a lawnmower, a standard gas lawnmower. Incredibly small amount of energy. And so this creates an opportunity for them to have an incredibly safe reactor with a very small footprint that hopefully would have regulatory requirements that would match it. And it could be a highly modularized life of reactor core that they could then use to kind of power a device and then remove the core when it's completed. And so this creates kind of a very different paradigm of a rapidly deployable, very small footprint nuclear technology for a specific application. Again, you wouldn't power a large chemical facility with an Aurora powerhouse, but it's interesting to figure out how it could be a specialty source of power in certain high-use applications. And so that really kind of brings us back to this kind of high level of takeaways. Really talking about how kind of a deep dive on advanced reactor technologies can provide really important insights on kind of what the goal of the technology is, what the potential use cases are, and what the safety case might be for regulation and technology development moving forward. A lot of these things just kind of become the starting point for talking with different companies and saying, okay, what specific things are they looking at, and how does that ultimately affect what the applications of this reactor technology might be? We can talk a lot about things like siting, about economics, about costs and deployment, but those might all be things for the Advanced Reactor 301 or kind of the next conversation we have. Hopefully, this is kind of a great starting point as you start to look at different advanced reactor companies in the space and try to evaluate what might be the right steps for you moving forward. So with that, I would love to